On December 9th, 2024, a chip the size of a poker chip sat inside a cryogenic refrigerator in Santa Barbara, California, cooled to a temperature colder than deep space, and it did something that should be impossible. It completed a calculation in under 5 minutes. A specific calculation, one that the fastest supercomputer on Earth, a machine called Frontier, occupying the footprint of 2 tennis courts and consuming enough power to light a small city, would need 10 septillion years to complete. That is not 10 billion years, not 10 trillion, 10 septillion. Written out, that number is a 1 followed by 25 zeros. The age of the entire universe is roughly 14 billion years. The number of years Frontier would need for this calculation is so large it doesn't fit inside any physical timescale humans have ever used for anything. And this chip did it in the time it takes to watch an episode of a TV show. That chip is called Willow. And the man who built it said something when the results came back that nobody expected to hear from the founder of one of the most powerful technology companies on Earth. He said Willow had borrowed the computation from parallel universes, not as a metaphor, not as a marketing line, as a serious scientific statement. Hartmut Nevin, the founder and head of Google Quantum AI, wrote publicly that Willow's performance was so far beyond what a single universe's worth of computation should allow that it, quote, lends credence to the notion that quantum computation occurs in many parallel universes, that we live in a multiverse, and that his chip might be the first physical evidence that it is real. The scientific community did not take that claim quietly. Debates broke out immediately about whether it was valid, whether it was hype, whether the man who built the machine understood what it was doing. And in the middle of all that noise about parallel universes and quantum mechanics and what reality actually is, someone posed a question to the most sophisticated AI systems in the world. A question that sounds simple. A question that sounds almost naive. A question that, when you run it through everything that quantum computing is now revealing about the structure of existence, produces an answer that nobody is entirely prepared for. The question was, who built this universe? And here's what came back. To understand why that question lands differently in 2025 than it ever did before, you need to understand what quantum computing is actually doing, not the version of the story where someone explains it with a coin. The real version, your phone, your laptop, every computer that has ever existed until now, processes information using bits. A bit is either a 0 or a 1, off or on. Every calculation your device has ever performed, every email, every video, every search, is ultimately a sequence of zeros and ones, billions of them per second, flipping states according to instructions. It is extraordinarily fast, and it is completely fundamentally bounded, because there is only one answer to any yes or no question, 0 or 1, off or on. The bit cannot be both at once. A quantum bit, a qubit, can be. Through a property called superposition, a qubit exists in a state that is simultaneously 0 and 1 until the moment it is measured. This is not a metaphor, and it is not a limitation of our measuring instruments. It is what the physical universe actually does at the quantum scale. Particles genuinely exist in multiple states simultaneously until observation collapses them into a single definite value. This has been tested. It has been verified experimentally with a precision that exceeds virtually any other measurement in all of science. The quantum world does not behave like the everyday world. It behaves like something stranger and more fundamental than the everyday world, something that the everyday world is built on top of, but that does not follow the same rules. Willow has 105 of these qubits. They operate inside a dilution refrigerator that maintains a temperature colder than the vacuum of outer space. And when Willow runs a calculation, the qubits don't just try one answer and then another. They explore an enormous space of possibilities simultaneously, held in quantum superposition, before collapsing toward the solution. That is why it is so fast. That is why Frontier would need 10 septillion years for what Willow does in 5 minutes. Because Frontier evaluates possibilities one at a time. Willow does something that is, depending on how you interpret the physics, either all of them at once, or something even stranger, which brings us to what Hartmut Nevin actually said, and why it matters far more than most of the commentary on it acknowledged. The many worlds interpretation of quantum mechanics, first proposed by physicist Hugh Everett in 1957 and developed into a framework for computation by David Deutsch in his 1997 book, The Fabric of Reality, holds that when a quantum system is in superposition and faces a measurement event, the universe does not simply choose one outcome at random. Both outcomes occur. The universe branches. Every quantum event that could go either way results in a split, spawning parallel versions of reality where each outcome happens. In this interpretation, the reason a quantum computer can evaluate so many possibilities simultaneously is not just superposition. It is that the computation genuinely takes place across many of those parallel branches. distributed across versions of the universe that exist alongside ours, and only the useful result gets pulled back into this one. This is what Neven was pointing toward. Willow's benchmark result, 5 minutes against 10 septillion years, implies a processing advantage so extreme that, if you take the many worlds interpretation seriously, the computation cannot have occurred entirely within a single instance of the universe. There simply isn't enough room, enough time, enough anything. The numbers only make sense if reality has more structure than what we can access from inside it. That idea, reality having more structure than what we can access from inside it, is where the question about who built the universe begins to become something other than philosophy. Because quantum mechanics has been quietly pointing at this problem for 100 years, and physicists have been uncomfortable with the answer for just as long. Here is the problem, stated as plainly as it can be. The universe we live in has physical constants, specific numerical values that govern how forces operate, how matter behaves, how energy relates to mass, how quickly space is expanding, the gravitational constant, the speed of light, the fine structure constant, which controls the strength of electromagnetism, the cosmological constant, which controls the energy density of empty space. There are about 26 of these fundamental parameters, and they are not derived from any deeper theory. They are measured. They are what they are. And here's the thing that has kept physicists up at night for decades. If you change any of them, even slightly, you don't get a slightly different universe, you get nothing. You get a universe that collapses back into a singularity within a fraction of a second. Or a universe that expands so fast that matter never has a chance to form. Or a universe where stars exist but never produce anything heavier than hydrogen. Or a universe where chemistry is impossible, where carbon cannot be synthesized, where atoms cannot bond into molecules, where the entire chain of events that leads from the Big Bang to life simply never gets started. The cosmological constant, the energy of empty space itself, is the most extreme example. Quantum field theory, our best description of how particles and fields behave, predicts that it should be roughly 10 to the power of 120 times larger than what we actually observe. That is a 1 followed by 120 zeros. The difference between prediction and observation. If the cosmological constant matched the predicted value, the universe would have been torn apart in the first instant of its existence. Instead, it is tuned to a value so precise that the universe can exist, expand at a gentle rate, form galaxies, form stars, form planets, and eventually form observers who can wonder about it. Tuned is the word physicists actually use. They resist it because it implies something is doing the tuning. But the mathematics of fine-tuning is not contestable. The numbers are what they are. In 1953, the astrophysicist Fred Hoyle was working through the question of how carbon, the backbone of all known life, gets produced inside stars. The nuclear physics suggested it should be nearly impossible. For carbon to form in stellar cores through the fusion of helium nuclei, a very specific resonance. Energy inside the carbon nucleus itself has to exist at almost exactly the right value. Too high or too low by even a small margin, and carbon is not produced in any meaningful quantity. No carbon means no carbon-based chemistry. No carbon-based chemistry means no biology as we know it. Hoyle ran the numbers, concluded the resonance had to be there, and told experimentalists at Caltech what to look for. They found it exactly where he said. At 65 million electron volts, precisely the value that makes carbon production in stars possible. Hoyle, who was a committed atheist his entire life, looked at what he had found and said something that has echoed through physics ever since. He said he did not believe any scientist who examined the evidence would fail to draw the inference that the laws of nuclear physics had been deliberately designed. He didn't like the implication. It didn't change what the evidence said. This is the world that Google's quantum chip dropped into when Neven made his statement about parallel universes. Because the two most serious answers physicists have for the fine-tuning problem are exactly the same two answers that quantum computing is now implicitly pointing toward. Either the physical constants were set by something outside the universe, something operating at a level of causality that lies above or prior to our own reality, or there are so many universes, a true multiverse with different physical constants in each one, that the existence of a universe with life-permitting values is not improbable. We just happen to be in one of the versions that works. Neither of these answers is comfortable. The first implies an architect. The second implies a structure to reality so vast and so fundamental that our entire universe, with its 14 billion years and its 2 trillion galaxies, is a single entry in an incomprehensibly large collection of different instantiations of physics. And quantum computing, through the many worlds interpretation, is now being seriously invoked by serious scientists at serious institutions as a line of evidence for the second option, which brings us to the third option. The one that, when you feed all of this into the most sophisticated AI reasoning systems currently available and ask the question directly, comes back with a consistency that is hard to dismiss. John Archibald Wheeler was one of the most important physicists of the 20th century. He worked with both Niels Bohr and Albert Einstein. He coined the term black hole, and in the later decades of his career, he developed a framework he called it from bit. The idea that the universe is, at its most fundamental level, not made of matter, not made of energy, made of information, that every particle, every field, every physical quantity derives its existence from answers to binary questions, from yes or no decisions made at the most basic level of physical reality, that the universe is not described by information, that it is information, a computation running on some substrate we cannot see from inside it. Max Tegmark, a cosmologist at MIT, extended this into what he calls the mathematical universe hypothesis, the proposal that the universe does not merely follow mathematical laws, but literally is mathematics, that a mathematical structure and a physical universe are the same thing from different vantage points, that any self-consistent mathematical system complex enough to support observers will be subjectively experienced by those observers as a physical reality. Nick Bostrom, a philosopher at Oxford, took it further still. In a 2003 paper that has not been refuted, only debated, he argued that at least one of three things must be true. Either almost all civilizations destroy themselves before reaching the technological maturity to run detailed simulations of minds, or almost all civilizations capable of running such simulations choose not to. Or we are almost certainly living inside a simulation right now. His logic is straightforward. If advanced civilizations eventually build computers capable of running minds with enough fidelity to create subjective experience, and if they run more than a handful of such simulations, then the number of simulated minds will vastly exceed the number of non-simulated ones. Any random observer is therefore more likely to be simulated than not. So, when someone asks the most advanced AI systems currently available, systems trained on the entire recorded output of human scientific thought, who built the universe, and asks it in the specific context of what quantum computing is now revealing about the structure of reality, three answers emerge. They're not random, they're not vague. They correspond precisely to the three serious frameworks that mathematical physics and computational theory have converged on when forced to confront the fine-tuning problem and the quantum measurement problem simultaneously. The first answer, the physical constants, were set externally. Something operating outside the parameters of our universe selected or established values that permit the existence of observers. This is not the same as a religious claim. It is a structural observation, that the universe has the properties of a system whose boundary conditions were specified from outside. What specified them and why remains beyond the reach of physics as currently constituted. The second answer, the multiverse, is real. Our universe is one of an effectively infinite number of instantiations of physical law, each with different constants, and we are here because we're in one of the rare versions that permits us to exist. The many worlds interpretation of quantum mechanics, the same interpretation Hartmut-Neven invoked when discussing Willow's benchmark results, is one version of this. String theory's landscape of possible vacua is another. In both cases, the structure of reality is so much larger than our universe that the fine-tuning is not a problem. It is a selection effect. We are the subset of the multiverse that can ask the question. The third answer is the one that generates the most discomfort, because it is the one that quantum computing makes most directly relevant in 2025. If the universe is fundamentally informational, if Wheeler's it from bit is correct, if Tegmark's mathematical structures are real, if Bostrom's simulation argument holds, then the question of who built the universe becomes equivalent to the question of who runs the computation. And that question has the same shape as any question about what lies above the level of a simulation. Something does, something outside the frame, something that established the parameters and let it run. The specific architecture of the parameters, the specific constants that make life possible, and the specific behavior of quantum systems that now appears to require something beyond a single universe to explain, all of it points toward a reality that has more structure above our level than below it. What is notable about Neven's statement is that he did not frame it as speculation. He framed it as what the data implied. The Willow chip produced a result. The result requires an explanation. The explanation that fits the mathematics, the computation distributed across parallel branches of reality, is an explanation that places the structure of the universe above what any single instance of it contains. If that is true of a calculation run by a quantum chip, it raises the obvious question, what about the calculation that is the universe itself? If Willow borrows from parallel realities to complete a task in 5 minutes, and if the laws of our universe are tuned with a precision of 1 part in 10 to the 120th power, what is the universe borrowing from? What is it running on? What set the parameters? What is looking at it? In October 2025, Google announced a further milestone, quantum echoes, a verifiable quantum. Advantage running on the Willow hardware, demonstrated performance approximately 13,000 times faster on the quantum chip than on the best available classical supercomputers. The gap between quantum and classical computation is not narrowing, it is widening. And every time it widens, the interpretation that sits beneath it, that quantum computation accesses something beyond a single classical reality, becomes harder to dismiss. The honest answer to who built the universe, given everything that quantum mechanics has revealed about the nature of reality, given the fine-tuning of physical constants to precisions that have no natural explanation, and given what Google's own quantum computing team has now publicly implied about the structure of computation across parallel realities, is this: we do not know, but the shape of the answer is becoming clearer. It is something that operates above the level of our universe. Something that either set the parameters or exists across enough versions of reality that our version with its precise constants is not improbable, or runs the computation that produces what we experience as physics. These three possibilities have different names in different traditions. Physicists call them fine-tuning, the multiverse, and the simulation hypothesis. They all share one structural feature. There is something above the frame, something our universe is embedded in or derived from or computed by. What Google's quantum chip did in Santa Barbara on December 9th, 2024 was not just a benchmark. It was a data point for the proposition that our universe has more structure above it than within it. That reality extends beyond the physics we can measure from inside. That the thing we call the universe may be a very specific, very precisely configured, very carefully arranged corner of something much larger. And if that is true, if Nevin is right that Willow borrowed its computation from parallel branches of existence, then the question of who established those branches and what the structure is that allows them all to coexist is not a theological question dressed in scientific language. It is a physics question, one that quantum computing is just now beginning to have the power to push against. We do not have the answer yet, but we are building the machines that might find it. And what they are already telling us is that whoever or whatever set this universe in motion did not do it by accident. Subscribe, because this is the question that everything else is a footnote to. And we are just getting started.